Hi guys, so here we're going to follow up the information that we learned about Le Chatelier's principle. So here we're just going to take the notes for this. Now if you weren't in class for the little seesaw activity or you didn't watch the video before this, make sure that you do because that kind of goes through and shows you some examples, so all of this will hopefully make sense after that. So you'll need your notes for this. And we're going to go through factors that affect direction of reaction, so if it goes in the forward or the reverse reaction. So those different factors are concentration, the temperature if it's an exothermic reaction, the temperature if it's endothermic, and pressure. And of course, pressure is only for gases. So for concentration, if we increase the concentration, it favors the opposite side. So if you had a pen or a pencil in your hand, which you should for the notes, put your fingers right in the middle for it, and then kind of rotate the pen. So if you increase the concentration on, say for example, the reactants, the left side of the pen would go down, and the right side would go up, so it favors the product side. And this does not affect the K equilibrium constant. If you decrease the concentration, so again, you have your pen in your hand, your fingers are right in the middle supporting it. If you decrease the concentration, say for the reactant side goes up, and it favors that same side. It favors the reactants. And of course, this does not affect the K. So the little picture down here at the bottom shows you what happens with cobalt 2 chloride. So the cobalt 2 chloride in solution is actually cobalt hexaaqua ions. That's the pink solution. When you add some Cl ions to it, so we could do that with calcium chloride, it becomes a blue solution, meaning it favors the products. On the right-hand side of the picture, it shows that if you have that blue solution, you add water to it. So you're pretty much adding more water, you're adding more products, it favors the opposite direction. So it favors the reactants. So here we're going to talk about temperature. So for exothermic reactions, the heat is in the product. So you might see kilojoules, joules, kilocalories, any of those values, and those would be for the products. If they give you a delta H value, it should just be a negative delta H value because you know that's going to be exothermic. So if you increase the temperature, so again, you have your pen in your hand, if the heat is in the products and you increase the temperature, that means that the product side goes down, the reactant side goes up, and it favors the reactants. This will also decrease the K value because as we looked in the equilibrium, so thing solving for K for the equilibrium video, we talked about how K is equal to the concentration of the products over the concentration of the reactants. So if we increase the temperature, we actually increase, the reactants will be increased. So that would go up, this would go down, and that K value would get smaller because there's a larger amount in the reactant side. Now if we decrease the temperature, so if the temperature side goes down, the decrease in temperature, meaning that if you have your pen in your hand, the product side goes up, and that favors the products. And that, of course, will increase K because, kind of going along the same lines over here, we end up having, let's get the erase, there we go. We end up having more products, less reactants. A greater numerator means that you have a greater value for K. Right? So for endothermic reactions, the heat is in the reactants, and the opposite happens here. So if we increase the temperature, the products are going to be favored, and again, heat is in the reactant side. You increase the K. If you decrease the temperature, that favors the reactants and decreases the K. So the picture on the right-hand side, if we have that pink cobalt hexaaqua ions, if you heat them up, the solution becomes blue, or it favors the right-hand side, or favors the products. That K value would go up. The picture on the right-hand side shows you if they cool down the products, you end up favoring the reactants in this case. So for pressure, this is of course for gases only. If you have liquids, solids, or aqueous solutions, pressure is not affected by this. So if you increase the pressure, it favors the side with the least number of moles of gases, and there's no effect on K. So if you decrease the pressure, you favor the side with the most number of moles of gases. And the reason for this is that pressure and volume are inversely proportional to one another. So if you increase the pressure, the volume goes down. So you have less space. So the picture on the bottom right shows you that if you had nitrogen atoms and hydrogen atoms and form ammonia from that, the Haber process, you end up having, if you increase the pressure, the volume goes down, so you see that piston going down, there's less space in there, so it's favoring the side with the least number of moles of gases, because on the reactant side we have 1, 2, 3, 4 moles of gases, and in the product side we have only 2 moles of gases. So again, if you increase the pressure, the volume goes down, the side which has the least number of moles is favored. If you decrease the pressure, that means the volume goes up. And so if we increase the if we increase the volume, we favor the side with the most number of moles of gases. And of course, there's no effect on K. Alright, so make sure that you guys know what happens with concentration, temperature, and pressure for K, what side is favored, what you'll make more of, etc. Have a great day, guys.